Yeah, velocity does show up all the time in biological applications. Typically speaking, if you're looking at, say, cells with flagella on the cellular level, how quickly they're moving is usually a decent sign of how lively they are. I don't know, there's probably some cool biological word for that, but I'm going to say not dead. So the idea is if you have a bacterial cell that's motile in an environment, you can see how well it's responding to its environment, how well it's thriving, based on how fast it's moving. So let's say you have a bacterial cell up here at the top at an initial position of 0, 23 micrometers, or 25 micrometers along the y-axis, or 25 micrometers upwards from the origin of your microscope. And then you see it swim down to a position of negative 10 micrometers in the x and negative 15 micrometers in the y. In other words, it's swimming down here. Again, not much of an artist, so let's just put it up here at the top, and let's just grab another one and put it down here at the bottom. Now, you've been told its initial and final position, so as always, your displacement is going to be from where you start to where you end up, and you know the change in time over which it occurs. You know that it takes 23 seconds for this to go about. So you need to calculate the average velocity of the cell. Now, to do this, keep in mind that whenever you're finding a velocity, it's going to be a vector, and you can find the vector velocity by taking the vector displacement and dividing it by the change in time, which I'm just going to write as t here. Typically speaking, I should probably use delta t, but for the sake of speed, we're just going to leave it. Now, the trick to dealing with this is actually to find the displacement. Keep in mind, the displacement is always final position minus initial position, where the final and initial positions are vectors. Now, we have these positions. Its final position is negative 10, negative 15. Again, we're going to leave the units out for right now, and we'll just put them in at the end to save ourselves some headache. And then we're going to subtract the initial position, 0, 23. Now, again, this is all nice and well. It's all in Cartesian notation. So all we need to do is take the x's, subtract them, then take the y's and subtract them. And doing so, I'll get negative 10. And here I'll get negative 38. And these are, of course, micrometers. And we'll just extend this so it looks like a micro unit. There we go, good enough. Now, when we find this displacement, we should make a quick sanity check. If we take a look at the signs of the things we have, our x is negative, so we're going left, and our y is negative, so we're going down. If these two things check out, they tell us basically we probably did the right mathematical operation. Now, with this displacement in hand, what we're going to do here is we're going to find the velocity. To find the velocity, what we're going to do is we're going to take this displacement that we have here, and we're going to divide it by our change in time. And what we found here was our change in time was 23 seconds. Now, keep in mind, there's a reason there's brackets around this Cartesian notation. We're actually going to divide both numbers that are inside there by the 23 seconds. So if we do this in x, keep in mind, we're going to keep the sign. We're going to take negative 10, and we're going to divide it by 23. And if you do so, you'll get negative 0.44, rounding, of course. And we can take negative 38 and also divide it by 23. And if we do so, we will get negative 1.65. Now, in terms of the units, we have micrometers divided by seconds. So we can't really cancel out or simplify a unit of distance and a unit of time. So we're just going to leave them as they are. If we needed a different unit, we could convert it. And of course, this is not a U, it is a micro symbol. And that's basically it. When you're dealing with average velocities, you can perform a proper weighted average, but most of the time, doing just final position minus initial position divided by the time, or the displacement divided by the time, is enough to find the average velocity. So if we really want it to be proper here, we put an average sign, which is just a straight bar over top of each of our velocities. If you have taken calculus, there is a difference between average velocity and instantaneous velocity, but that is a lesson for a slightly different course.